So Unit 5 review number 1. Are we ready?
No.
Yeah, we are. The probability of rolling 2 6-sided dice and having the sum on the top dice equals 7 is 1 out of 6. Interpret this probability. What does that mean?
You have to say what that means.
If we roll
Many times.
2 dice many times.
So we have to say many.
Yeah.
Hold on, this.
Yeah. Wait, actually, that's the only.
What?
Like if we only use one many, we're gonna get like
Many.
1 point.
I'm going wrong. Oh gosh.
If we roll 2 dice many times,
I don't remember this.
about 1/6 of the rolls will equal 7. If we so that is the that's the way that you show that you know that probability is a long-term probability, is by saying that it's many times. We don't want to say that if we roll 2 dice that 1/6 of the rolls will equal 7, because if we roll 2 dice 6 times, I'm not guaranteed to get a 7.
Doing anything?
No. Yes.
What do you want?
So you roll 2 dice 6 times. Are you guaranteed to get a sum of 7 once? This is literally what I was just saying about why we put in the many. So if I roll it 6 times, am I guaranteed to get a sum of 7 one time?
No.
Nope.
Probable. No guarantee.
No guarantees.
And then it says explain.
No guarantees because
There's a lot of variability.
there's lots of variability. There is a lot of variability in short run probability. That is exactly right. There's lots of variability in short run probability. Cool? Cool. To pass the time during a long drive, you and a friend are keeping track of the makes and models of cars that pass by in the other direction. At one point, you realize that among the last 20 cars, there hasn't been a single Ford.
Thank God. That's a good American person right there.
Currently, about 16% of cars sold in America are Fords. Your friend says, well, the law of averages says that the next car is almost certain to be a Ford. Explain to your friend what he doesn't understand about probability. All right, so the law of averages is a myth. Each car has a 16% chance of being a Ford. No law of averages. Yes, sir.
So, if a question talked about a baseball player batting a bunch of times, they said the law of averages, should he get one? It's always no.
Yep, that's correct. Very good. All right, number 3. Man, look, we're already on number 3. Already on this. That's fine. All right, so here we go. Suppose you choose a random U.S. resident over the age of 25. The table below is a probability model for the education level that select person has attained based on data from the American Community Survey from 2006 to 2008. All right, so the education level attained: no high school diploma or GED, some college, a bachelor's degree, or the graduate or professional degree. What is the probability that a randomly selected person has a graduate or professional degree? Basically, what goes in where the question mark is. Okay, so let's add them all up and see what they equal, and then what do we do with that?
Oh, I got it. I did it. And then just 100 minus that.
Yeah.
Or just 1. Because.
Yep. So we're gonna take all of those and add them up. So 0.2 plus 0.22 plus 0.29 plus 0.19 equals a number. It is 0.9. So, what is the question mark? So 1 minus 0.9 is 0.1. So that is what goes there, 0.1. All right, what is the probability that a randomly selected person has at least a high school diploma? How would you find the probability that the person has at least a high school diploma?
Would you just add values?
You would just add all those probabilities from high school diploma and up. So 0.22 plus 0.29 plus 0.19 plus 0.1 equals 0.8. Is there a different way to do that problem?
Always.
1 minus the 0.2. 1 minus the 0.2 would also give me 0.8. Very good, very good, very good. Okay. Let's keep going. Last Saturday at Pascal's Pizza and Wings, 60 customers were served over the course of the evening. 52 customers ordered pizza and 16 ordered buffalo wings. 12 of these customers ordered both pizza and wings. Suppose we select a customer from last Saturday at random. We're going to create a Venn diagram. P is that they ordered pizza. W is that they ordered wings. Pizza and wings. All right, so in the middle here, we've got pizza and wings. How many of the customers ordered pizza and wings?
60. Wait, what? Oh, it says 12.
12 of the customers ordered both pizza and wings, okay? Now look, it says here that there were 60 total customers and 52 ordered pizza. That's the total pizza circle. So I've already taken care of 12 of those 52. So how many got pizza but not wings?
Which is probably 40? 38. Wait, no, it's 50.
Nope.
It's 38.
Wait.
52 total got pizza, and I've already labeled 12 of them.
So it's 40.
40.
Wait, and it's 52, not 50.
Oh.
52 customers.
I didn't want to.
I was really struggling with y'all's math there.
No, I wasn't.
All right. It says that 16 ordered buffalo wings, but that doesn't mean they only got buffalo wings. That means that they got buffalo wings, but they could have also got pizza. In fact, 12 of them did. So how many of them did not get pizza, but they did get wings? 4. Is that everybody?
No.
No. There are, for some reason, are some people that went to this pizza and wing place and did not get pizza or wings. Weird.
Taco.
Pizza compliment and wing compliment. Now, there were 60 total customers. So if I take 60 and I subtract the 40 and the 12 and the 4, 60 minus 40, 12, and 4. 4. There are 4 people that are at a pizza and wing place not eating pizza and wings. Okay, the question here says, what is the probability that a randomly chosen customer did not order wings or pizza? I think we just figured that out. The probability of pizza compliment and wing compliment is 4. Now, here's the deal. Plot twist right here. It asks for a probability. I just gave a number of people. So how do I fix it?
Well, you take 100 and then divide that by 60, because that's how many customers are, and then multiply it by 4.
Or I could just divide this by 60.
But that's boring.
That is boring, but your way is weird. So
That's just how it would work.
you're not wrong. It would work, but why? All right, so 4 over 60 is some number. What is it? 1 over 15, which is some other decimal. I don't know what it is, though. I'm not a human calculator. So 1 over 15. So yeah, 0.067.
It's not funny, man.
I don't understand the complimentary thing.
What?
Like,
It just means not pizza and not wings.
so like if
I
there's a
think
C,
it says
it just means that it
complimentary.
That
doesn't.
means not.
Okay.
That means
Oh,
not
you
that
mean
thing.
the little C thing?
Yeah.
Oh, yeah.
No, the other C.
No, I didn't know what you were talking about. I thought you were I didn't know that's what it's called, actually. You're right. I talk too much when I'm tired, man.
All right, next problem.
Let me take a nap.
The table below gives the counts in thousands of earned degrees in the United States in a recent year, classified by level and the gender of the degree recipient. This looks really, really familiar. This was on the 5.3 workout. Whoops. List 2 mutually exclusive events for this chance process. Okay, these questions are different, so that's fine. All right, list 2 mutually exclusive events for this chance process. What does mutually exclusive mean? They cannot happen at the same time. Now look, I'm just going to tell you guys, if you look at any column and any row, they all have numbers in them. So none of those, like a column and row combination, is not going to be mutually exclusive. So looks like you got to think outside the box here. Look at 2 rows or 2 columns. I cannot be in the female row and in the male row. So 2 mutually exclusive events would be the females and the males. You can't be in both of those. 2 mutually exclusive events could be a bachelor's degree and a master's degree, or it could be a bachelor's and a professional, or it could be a professional and a doctorate, because we're only allowing people to be in one particular category. All right? So when you are asked for mutually exclusive events from a table, you're going to want to look at columns that are side by side or rows that are together. So any of those 2 would work, but the most obvious one is the females and the males. Female and male cannot be true at same time. So those would be mutually exclusive. All right, what is the probability that the person selected earned a master's degree? There's no condition here. We're just asking, out of all these people, what's the probability that somebody earned a master's degree? 365 out of 1626. 365 out of 1626. .2245. Alrighty. Next question says, what is the probability that the person selected earned a professional or a doctorate degree? Now, are those 2 events mutually exclusive? They are, okay? I can't be in both of those columns at the same time, so I can just add those 2 numbers together and get this probability. So I can take 74 over 1626 and add 42 over 1626. $74 plus 42 is 116 over 1626. And so there's our probability, 0.0713. Since those were mutually exclusive, professional and doctorate degree, I could just add up their numbers and not be worried about it. Okay, what is the probability that a selected person is female or earned a master's degree? Are those mutually exclusive?
No.
They are not. So I'm going to have to be careful here that I don't double count. So, how many females are there? 856 out of 1626. How many master's degrees are there? 365 out of 1626. But included in both of those, I have included the females that have the master's degree in both of those. So I've got to subtract off that overlap so that I'm not double counting it. So I've got my females plus my master's degree, and then I took off where I've double counted it. So
Where did you get the 194 from?
the
The
194
master's,
is
so
the
female.
overlap here, the females with the master's degrees.
Okay.
Couldn't you just put like 171 for the males then?
You could. Yes.
Yeah.
Yeah, there's a couple different ways to do it. Yep. So I've got 856 plus 365 minus 194. That is 1027 out of 1626, which is 0.6316. All right, for number 6, we're going to look at some old unit stuff. All right, so just kind of keep this fresh on your mind. These are some of the big ideas, the things we really want to make sure you guys are remembering. So number 6, the first one says, the stem plot below shows the number of home runs hit in 2008 by members of the Philadelphia Phillies, who won Major League Baseball's World Series that year. Each of the 13 players who appeared in at least half of the Phillies games that year are included. All right, so we have our stem plot here. It tells us here that 4/8 is a player who hit 48 home runs. And we are asked, what is the 5-number summary for these data? So we have to remember what the 5-number summary tells us. 5-number summary tells us the minimum, quartile 1, the median, quartile 3, and the maximum. So a couple of these numbers are really easy to find. The minimum, obviously, would be the 0. The maximum would be the 48. Okay? So I can go ahead and mark out, I know that A is not going to be an option, and I know that D is not going to be an option. Okay? And so now my median. Obviously, I can quickly look at my answer choices and tell that my median is 11, but I'm going to go ahead and do the whole marking off thing. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So yes, again, my median is 11. Now, I need to find quartile 1 and quartile 3. So quartile 1 is the median of the lower half of the data. So the lower half of the data is this half here. So I need to find the median of that lower half. So it looks like if I do 2 and 2 here, that I now have 2 numbers, a 4 and a 9, that are the lower half median. So I need to average those. So I would have 4 plus 9 divided by 2, and that's going to give me the average, which is going to be 6.5. So with that, we now know the answer is C, but I'm going to go ahead and find Q3. Q3 is going to be the median of the upper half of the data. So 1, 2, 1, 2, and so I would need to average 24 and 33. So 24 plus 33 divided by 2 would give me 28.5, which confirms that C is the right answer. All right, let's look at the second one. Oops. All right, the second one says, a sample of production records for an automobile manufacturer shows the following figures for production per shift: 705, 700, 690, and 705. And we are asked to find the standard deviation of this sample. Now remember, for standard deviation, we're just going to want to go ahead and use our calculator instead of trying to use the formula, because the formula was a little scary. And so we're just going to use our calculator. So we're going to put this data into L1. We want to input data into L1. To do that, you just go to Stat Edit, and you put your data into L1. Then you're going to go to Stat, Calc, and it's number 1, which is the one variable stat. And once you get that calculation, then you will look at what the S sub x is, which is what the standard deviation will be. And so when we plug its data in and we find that standard deviation, then we can see that the that the standard deviation is 7.07, which is B. All right. Number 3, the 5-number summary, again, for these summary statistics is, for the statistics exam, is 11, 35, 61, 70, and 79. So again, remember that means that this is the minimum, quartile 1, the median, quartile 3, and the maximum. In all, 380 students took the test. About how many students had scores between 35 and 61? Remember that the 5-number summary cuts my data into 25% sections. So in between each of these numbers, there's 25%. So in between 35 and 61, there is 25% of the data. And so if 380 students took the test, then all I need to do is find 25% of 380. And so when I do that, I find that the answer is 95. Alrighty, and then for number 4, 40-pound bags of bird seed do not have exactly 40 pounds of seed, but the weight of seeds is approximately normally distributed with a mean of 40 and a standard deviation of 0.25. Which of the following is the best estimate of the 90th percentile? It tells me I have a normal distribution, and pretty much every time I'm told that, I'm going to draw it. And we have a mean of 40. And we have a standard deviation of 0.25. So we have 40.25, 40.5, 40.75, and then we have 39.75, 39.5, and 39.25. So in order for it to be the 90th percentile, that means that I have to have 90% of my graph shaded from the lower side. When I get to the 40, that's 50%. The next section here, remember this is 34%, so I'm at 84%. And then I wouldn't go quite to the next line. It's going to be somewhere here, okay? But what I do know is that the lower area here is 0.9. So I know the area and I want the boundary. That sounds like an inverse norm problem. Inverse norm, the lower area here is 0.9. The mean of this distribution is 40. The standard deviation is 0.25. So I'm going to go to second vars. I'm going to go to inverse norm, and I'm going to plug in an area of 0.9, a mean of 40, and a standard deviation of 0.25, and we get an answer of 40.32, and so that is closest to 40.3. All right, let's see what we've got next. An ecologist who was studying starfish populations collected starfish of the species Pisaster. He was interested in the distribution of sizes of the species of starfish. One measure of size is the arm length. Below is a cumulative relative frequency graph for the arm length in centimeters of 102 Pisaster individuals. What are the approximate values of the median and the interquartile range of this distribution? So what you'll need to remember for this one is that the median is where the 50% mark is. The median is where the 50th percentile is located, 50% mark. And so we want to go and find where's the 50% mark. And we'll go over to the graph and then down from there. And we look like we're about at 15 centimeters. And so that takes off B, C, and D. For IQR, we're going to want to remember that for IQR, that is where we have the 75th percentile minus the 25th percentile. Minus the 25th percentile. So if I go to my graph and I look about where 75 is, and I go down from there, that's at about 16. And then my 25%, that's at about 12. Then my IQR would be 4. So remember, this problem, part A, is telling us to be careful and remember that IQR is a single number. It is actually when you do the subtraction of Q3 minus Q1, okay? And so that's how we get the IQR. All right, our next problem. We have a company that is packaging soap powder and it's labeled giant size 32 ounce. The actual weight of soap powder in a box is normally distributed with a mean of 33 and a standard deviation of 0.8. What proportion of the packets are underweight? They weigh less than 32 ounces. So again, I have a normal distribution, so I might as well draw it. I've got 33 is my average, and I've got a standard deviation of 8.8. So we've got 33.8, we've got 34.6, 35.4, and we've got 32.2, 31.4, and 30.6. All right, what proportion are underweight? They are less than 32. So let's say 32 is about here. I'm trying to find the area that is less than 32. So this is going to be normal CDF, because I am looking for the area this time. So normal CDF. The lower boundary is negative infinity. Negative infinity. The upper boundary is 32, the mean is 33, and the standard deviation is 0.8. I plug this into second VARS, normal CDF, and don't forget your E right here needs to be the scientific E, which is second and the comma, which is above the 7. And I go to plug that in, and my answer is 0.1056, and so that is closest to A. Our final question here, the correlation between number of service calls and number of copy machines leased is 0.86. About what percent of the variability in number of service calls is explained by the linear relationship between number of service calls and number of machines? So what you have to do on this problem is recognize what was being told to you and what you're being asked for. So we were told the correlation, which is R. We're being asked for the percent of the variability. We're being asked for R squared. So R squared is literally, I can just take R and square it. And when we take R and we square it, we get 0.7396, which is about 74%. And that wraps up our section on the old units, and then we'll get back to Chapter 5, Probability. We have another problem that was on our workout, you guys. This was on the 5.3 workout, but we're going to do it again anyway. Suppose a person is having 2 surgeries performed by the same at the same time, but by different operating teams. Assume unrealistically that they are independent of each other. When you have 2 things that are independent, what are you probably going to have to do with those 2 numbers? Multiply them, okay? And when you multiply them, you'll get the probability of their overlap, the and. If the chances for success on surgery A are 85%, so the probability for surgery A to be successful is 0.85, and the chances for success on surgery B is 0.9. What's the probability, careful here, that they both fail that they both fail
Yeah, okay, now.
independently of each other. So the probability that A is successful is 0.85. What's the probability that A fails?
The rest.
That's the probability of A complement, so not success. That is 0.15. And then if the probability of B being successful is 0.9, what's the probability that B fails? 0.1. Now, I can find the probability that they both fail. That would be the probability that A fails and B fails. Since these are independent, I can just multiply their probabilities and not worry about anything else. So 0.15 times 0.1 is 0.015. That is the probability that both of them fail independently of each other.
I'm confused on what independent means.
Independent means that they do not.
Are we still, we're doing it?
Parking for students at Central High School is very limited, and those who arrive late have to park illegally and take their chance to get a ticket. So the events here are not late and illegal. The events here are
Illegal.
parking illegally and then getting a ticket.
Ticket.
Okay? So, Joey has determined that the probability that he has to park illegally. So he's going to have to park illegal or not illegal.
Because you have to park over there.
Right. Then he's going to either get a ticket or no ticket. He's either going to get a ticket or no ticket. Okay, cool. So this situation is this: illegal and a ticket. So the probability of parking illegally and getting a ticket, that would be that one. The next one would be that he parks illegally and does not get a ticket, so ticket complement. The next one would be the probability that he does not park illegally, so that would be illegal complement, and he does still get a ticket. And then the probability that illegal complement and ticket complement. Okay. So, what was told to us in the problem? Let's read. It says, Joey has determined that the probability that he has to park illegally and that he gets a parking ticket is 0.07. So, he parks illegally and gets a ticket. That is 0.07, which goes right there. He recorded data last year and found that because of his perpetual tardiness, the probability he will have to park illegally is 0.25. Okay, so the probability he has to park illegally is 0.25. So that goes right there. What's the probability he does not have to park illegally? 0.75. Okay, cool. Suppose that he arrives late once again. He's arriving late again. What does that mean he's going to have to do? He's going to have to park illegally. Suppose that he has to park illegally again. He's late once again, and he had to park in a no park zone. Can you find the probability that he will get a ticket given that he was illegal? So look, here's what we've got here. Remember, to find these final probabilities, we just have to multiply the tree, the branches of the tree diagram here. So 0.25 times something equals 0.07. So could I find that number? Yeah, how? By dividing. You got it. So all I have to do here is I know that 0.25 times some number, x, is 0.07. So I just have to divide by 0.25 in order to find this answer. This is going to be the probability that he's going to get a ticket given that he did park illegally, which it says he did have to park illegally this day. So 28%. There's a 28% chance that he's going to get a ticket given the fact that he just parked illegally. Cool? Cool. The probabilities on the bottom didn't even matter, so that was nice. All right. Let's look at number 9. Is there a relationship between gender and student preference? In Miss Lakey's first period class, 32 students. There are 15 males, 18 students prefer math, and 8 male students who prefer, does that both say math? 18 students prefer math, sorry, and 8 male students who prefer math. There we go. We're going to make a two-way table summarizing the data. What are the two different variables here? Male and whether they like math or not. So, well, let's see. We're going to let M be male. What should we use for math? Because we sure can't use M again.
MA.
MA?
Just kidding. That would not
Well,
help.
A for A.
C? Okay, we'll use C.
Pass for sucks.
What?
Wow. Really?
Yes.
We should use F. I won't say why. All right.
Friends.
C for math. All right, so here we got a two-way table. We're going to have male, and we're going to have male complement. We're going to have math, or C, and C complement. Okay. In Miss Lakey's first period class, there's a total of 32 students. Where does that go? Total, 32 students. 15 are males. So I got 15 males. So how many females are in that class? Or non-males?
What? I don't know how many. 18, that minus 15 is 3. Oh no, that says prefer math. There's 32 students. So then
There's 32
it's
total
17.
students. 15 of them are
17.
male. So how many of them are not male? 17. Okay, cool. Now it says that 18 prefer math. 18 prefer math. So if 18 of the 32 prefer math, how many do not prefer math?
Nope.
14.
That's what I said. Yeah, 14.
And finally, it says that 8 male students prefer math. So that's where male and math overlap. 8 male students prefer math. All right, so how many non-male students prefer math? How many male students don't prefer math? And how many non-male students do not prefer math? Perfect. All right, let's answer some probability questions. What's the probability that a randomly selected student prefers math if the student is female? That's just a different way of asking the given question. This is the probability that they prefer math given that they're female. So, given that they are not male, what's the probability they prefer math? 10 out of 17. What is 10 out of 17?
0.58.
All right. Suppose the student prefers English. What's the probability that the student is male? Suppose the student prefers English, so they prefer not math. So that's here. What's the probability that the student is female? 7 out of 14, which is a half. That is the probability of being female given they preferred not math. That was the formula we just used.
I don't know what you said, but I'm sure it was funny.
Is there a part D?
Are they gone? Oh.
Is there a part T?
Darn.
They're not.
You almost done?
Almost. Oh, okay. Next thing says, are the two events male and prefer English mutually exclusive? Male and prefers English, so not preferring math. Why not? They overlap right there. How many of the males don't prefer math? 7. So there's 7 of them. Okay, so because of that, they are not mutually exclusive. So, no, Yeah, I know. Males and not math, aka English, overlap 7 times. Suppose we choose one of the students in the sample at random. Are the events male and math independent? So this one we have to check. Does the probability of male given math equal the probability of just male by itself? If so, then that means that liking math has no bearing on your gender. So, what was the probability of male given math? Did we already find that one?
What?
What was it? There was 8 out of how many? 8 out of 32. No.
Wait, what?
Sorry, just try that again. Given that they like math, how many of them liked math total? Total was 8? How many total people liked math?
Oh.
The C.
18.
18.
Over 30.
How many of those 18 were males? 8. So 8 out of 18. Now, does that equal the number of, or the probability of male? What was the probability of being male in this problem? 15 out of 32. Oh my gosh, what are these numbers equal? What is 8 out of 18?
It's not the same.
They're not the same?
Wait, maybe? Who knows? I think they are. What's this?
8 out of
Yes, I
18.
think they are.
8 out of 18 is 0.444. 15 out of 32 is 0.468. These are not independent. All right, a manufacturer of holiday lights knows that 1% of its lights are defective in some way. Suppose an inspector randomly selects 444 lights for an inspection. Assuming the lights are independent, what is the probability that at least one of the selected lights is defective?
Given the law of averages, I think it should be.
All right, what's the probability of defection?
1%.
0.01. All right. Now, we want to know the probability that at least one of 444 are defective. You guys, that's a lot of probabilities to calculate. So let's use our complement rule for at least one. 1 minus the probability that none of the 444 are defective. So, this is the probability of defective. What's the probability that it's not defective? Okay, so the probability of not defective is 0.99. Alrighty. Well, if none of the 444 are defective, how would I find that number?
To the
0.99 to the 444th power. That's a ginormous probability that I can't do by myself, so I will use a calculator. 1 minus 0.99 to the 444th power. Here's the probability that at least one of these things is going to be defective. It's a big number. 0.988. It's almost guaranteed that at least one of them is defective. But you got to think about it this way. I'm talking about 444 trials. Of course, at least one of them is going to be defective, right? Like that should not be shocking.
Wait,
Cool?
Why'd you put the 444 as like an exponent?
Yep, because none of the 444 are going to be defective. So that means the first one is not defective. That's a 99% chance. The second one is not defective. That's a 99% chance. And so I have 99% chance 444 times. So that's to the 444th power. Last page, you guys. How we feeling?
Tired.
Still tired.
All right, a hospital is testing patients for a certain disease. If a patient has the disease, the test is designed to return a positive result. If the patient does not have the disease, the test returns a negative result. No test is perfect, though. 99% of patients who have the disease will test positive. 5% of patients who don't have the disease will also test positive. 10% of the population in question has the disease. If a random patient tests positive, what's the probability that they actually have the disease? What should we do? Tree diagram. Let's go. So look, they either have the disease or they do not have the disease. It tells us that 10% of the population has this disease. That means that 90% do not have this disease. All right. Now, when you have the disease or you don't, you're going to go get a test. And you're either going to be positive or negative. So it says here that 99% of patients who have the disease will test positive. So 99% of patients who have the disease will test positive. So what percent will test negative for if they have the disease? 0.01. It says that 5% of patients who don't have the disease will also test positive. So that means that 95% will test negative when they don't have the disease. If a random patient tests positive, what's the probability that they have the disease? Here's what we're asking here. What's the probability that you have the disease given you got a positive result? The probability you have the disease given you have a positive result. So anytime you have conditional probability, the probability that you have the disease and you get a positive divided by the probability of a positive test result. All right, can we find the probability of having the disease and getting a positive? We just multiply those two things. This would be the probability that you have the disease and you get a positive. This is 0.1 times 0.99. What is 0.1 times 0.99? 0.099. All right, so that's going to go on the top of the fraction. Honestly, guys, this is the part where most people mess up. Because the question now is, what is the probability that you get a positive result? What are the different options for ways you could get a positive result? You could have the disease and get a positive result, which we know that probability. Or you might not have the disease, but still get a positive result. So I need to add those two probabilities together. So that means I still need to find, this probability right here. So this is the probability that I do not have the disease and I still get a positive result. That's 0.9 times 0.05. So the total of those two is the probability that I get a positive result. Because in either of those situations, I have gotten this positive result. So I do need to add those two things together. So the probability of a positive is those two things added together. So 0.099 plus 0.045 is 0.144. And that's what's going to go on the bottom of this conditional probability fraction. 0.099 divided by 0.144. Cool? So, doctor comes in, says, hey, you got a positive test. What's the chance you actually have the disease? 68%. Alrighty. Let's look at number 12. An airport screens bags for forbidden items, and an alarm is supposed to be triggered when a forbidden item is detected. Suppose that 5% of bags contain forbidden items. If a bag contains a forbidden item, there is a 98% chance that it will trigger the alarm. If a bag does not contain a forbidden item, there's an 8% chance that it triggers an alarm. Given that a randomly chosen bag triggers the alarm, what's the probability that it actually has a forbidden item? What does this sound like you should do? This is literally just like that last problem. It's just a different context to the problem. All right, so we either have a forbidden item, or we do not have a forbidden item. And we're either going to get an alarm or no alarm. All right, it says here that 5% of bags have a forbidden item. Terrible people. That means 95% do not have a forbidden item. If the bag contains a forbidden item, there's a 98% chance that we're going to have the alarm go off. So having the item, 98% chance of the alarm. Not having the item, having the item but no alarm goes off, so we get away with having this forbidden item. Tisk tisk. If the bag does not contain a forbidden item, there is an 8% chance that we still get the alarm. And if we do not have the forbidden item, there is then a 92% chance that we do not get the alarm. All right, again, here's what the question is for this, or what we're being asked here. What is the probability that we have a forbidden item given that we got an alarm? That's what's being asked. So what I need to do is I need to find the probability that we have an item and we get the alarm divided by the probability that we get an alarm. This works exactly the same way, y'all. I have the item and I get the alarm. I'm going to multiply those two things together. So that's going to be 0.05 times 0.98. This is the probability that we have the item and we get the alarm. 0.05 times 0.98. That is 0.049. So that's the top of the fraction. And again, how could it be that we get an alarm? It could be that we have the item and we get the alarm, which we already have there. Or we might not have the alarm, have an item, but we still get the alarm. 0.95 times 0.08. That would be 0.076. So the probability of an alarm total are those two things together. .125, and I just divide these two things, and 0.392. So the alarm goes off. What's the chance that I actually have a forbidden item? It's 39%. Cool? Last problem. Dirk Nowitzki. He's the GOAT. He has made 87.9% of his free throws during his long 20-plus year career. So the probability that he makes it is 0.879. Assume that each shot is independent. If Dirk attempts 30 free throws, what's the probability that he misses at least one of 30 is missed? All right, so the probability of at least one of the 30 is missed. Now look, we know the probability that he's going to make it, right? So this is at least one of the 30 is missed. So this is going to be 1 minus the probability that none are missed. So this one's slightly different from what we've done before because we actually already have the probability that it's not missed. We have the probability that he's going to make it, which is exactly what we need. So all we have to do here is take 1 minus 0.879 to the 30th power. Huh?
I knew it was different.
Just like did it what we did for 10.
Right, yeah. So the only difference here was that this one, we actually already had the probability that we needed. So 0.979 is our probability. Cool? Cool.